Hello, hello. Are we? Hello, May. Hello. Hi. Thank you. Hello. Great to see you. Okay, you're like the one. And hello. Well, I guess you're the. Okay. Well, hello, everyone. Hello, May, and everyone. Okay, we will start. Hold on 1 second. Hello, Eric. Okay. Wait, okay. Hello. Now we're talking. All right. All right. So hello, May. Hello, Eric. Excuse me. Hello, Elizabeth with an S. Good afternoon, Noel with an N. Hi, Lizzie with a Lizzie. And also, I guess I'm officially sort of weirdly saying hi, Maisha, because she sent me a hi in advance. I don't know if that counts with this whole, but John's not here either, so I don't even know how. All right. Anyway, hello, Stephanie, and hello. That's everybody. Okay, let's get straight to business. Business is, whoop, is not that. Business is this. Okay. There's this equation in the middle of the board here that I've now written in anticipation a couple of times, the last couple of classes, and the real goal is to get to it today. We're really going to talk about it today. And then it leads to these things at the bottom, which we won't probably get to today. But where is this all coming from? It's all coming from the fact that what we are finally up to, after weeks and weeks of buildup that does occur every semester this way, we are finally up to question 9 of homework 1. And yes, strangely, it does take us that long to get there. And question 9 is the point of homework 1. It is really the point. It's actually question 9 is a big topic unto itself, and it's sort of what many of your lab experiences right now are about or have been about. And even this question 9, believe it or not, we're not going to finish. I'm telling you right now, we're not going to actually get an answer to it today. And I apologize in advance, but it's actually that deep of a question. This also means that, oh, people are coming. This also means that, unlike all, that at this point, everybody's handed in the homework and tried and all of that. And I would hope that everybody sort of did get answers and understand the answers to all the parts of the homework up until question 9. But and I know someone just came in. Where do they go? Someone just came in. I can't. Oh, here. Okay. Okay. But to be honest, with question 9 is a big enough deal that it's totally acceptable and understandable if you tried it to a certain point and then stopped, or you tried it to a certain point and then got it wrong, or something like that. Like there are ways to get question 9 right by poking around the web and finding certain things that maybe certain people wrote down from the web. And if you understand what you wrote down from the web, I mean, from the internet, then Quark bless America. That's great. But I hope that we only write things down that we understand. And I'm here to say that, yeah, question 9 is a big discussion. It was never expected that you would just have the answer like right off the top of your head or something like that. It was expected and hoped that you would think it through and see why question 9 is an issue. And then I'm here today to start resolving that issue. So anyway, so we're on, again, for people who just joined, we're on question 9 of homework 1. It is the point of the whole homework assignment. What is question 9 of homework 1? Well, as it says at the top of the screen here, what it is, okay, at t equals 1, what's x? Very simple sounding question, a very deceptively simple sounding question. Like literally at t equals 1, what's x? Like, and again, correct me if your understanding is different, but I believe that that's question 9. And so what I'm noting here in the black writing is like, what if we back up for a second? There's nothing particularly special about t equals 1. Like t equals 1 means the first second of this back and forth motion of the mass on a spring. We've asked all of the prior questions, all questions 1 through 8, to build up an understanding and a set of expectations and a set of principles surrounding this type of oscillation that we're seeing in the homework of an object going back and forth cyclically. Anything that goes back and forth and back and forth, or anything that has a certain sort of repeated motion is known as oscillation. This particular type of motion, in fact, I'm going to write this right now, but anything that goes back and forth is called oscillation. I could be walking back and forth at the front of the room, and I could be doing it in a very spastic, sort of random way, where I could walk 5 feet that way and then 3 feet the other way, and I could walk at this speed to the left and then a different speed to the right. If I did that, we would call it oscillation, but it'd be very random, unpredictable, unsteady, unpatterned oscillation. It would just be general oscillation. The kind of oscillation that we're looking at in this homework sheet up until now, this very patterned, very steady, very predictable, very symmetric oscillation happens to be known as, and we're going to call it more and more, it happens to be known as harmonic oscillation. That's what I want to write right here. Sorry. The kind of motion that we're looking at in this entire homework sheet and in the early labs of the semester is a very patterned, steady type of oscillation known as harmonic. We're asking, and again, the purpose of questions 1 through 8 was really to say, like, any kind of patterns that you think you see in this motion, or any kind of patterns that you might expect to be going on, like it's getting faster and faster to equilibrium, then it gets slower and slower, and then it gets faster and faster, getting the same exact way, and then gets slower and slower. Or that the acceleration is getting lesser and lesser, and then getting more and more, and then getting lesser and lesser, and then getting more and more. Any of these patterns that you think are unfolding, we're here to say, oh, they are unfolding, and you can rely on them. And in fact, there's even more patterns than that. And oscillation that is that heavily patterned and that heavily symmetric is called harmonic oscillation. We're now, for the first time in this sheet, asking a very straightforward sounding question about harmonic oscillation. We're saying, okay, if someone names the time, can we name the place? Like if you specify a certain t value, a certain point in time, can we say where the oscillator is going to be at that moment? That's a very fair question to ask. In fact, that's like the question that's always being asked in physics in one way or another, is where is something going to be when? There's nothing special about t equals 1 second. We're just asking, really, in general, can we derive a mathematical expression, a function that maps t as the independent variable to x as the dependent variable? Like, so that's why I wrote in black here on the first page. What we're really looking for here, like, yes, ultimately we're looking for a numerical answer to question 9. Ultimately, we'll know we have finished question 9 when we get a numerical answer. And by the way, for those people who are like dying of the suspense or whatever, I believe the final answer, it does turn out to be 0.116 meters, I believe, if you're like interested. But really, honestly, I don't really care what the final numerical answer is. What I really care about is, can we come up with an expression such that for any t we plug in, it would spit out an x? We are really looking for a function here. That's actually the point of every lab in physics. And it's ultimately the point of any good question in sort of higher level physics, like physics 204. We used to think that I used to think that physics was about using equations and plugging into equations to get answers to questions. It turns out that physics is really about developing, creating, discovering those equations, not using them, but deriving them. So our goal here in question 9 really is, can we derive x as a function of t for this situation of harmonic oscillation? I'm going to say one last thing about that and then move on to the next page. Often, I'm going to say, In physics, there's lots of equations. Obviously, there's lots of functions. It's all about equations and functions in physics ultimately. But I'm here to say that whenever you get an equation that specifically maps t as the independent variable to x as the dependent variable, we tend to call that in physics specifically an equation of motion. Again, like there's lots of equations in physics and lots of them are about motion, like all of them are ultimately about motion, but specifically any equation that produces x as a function of t is ultimately known as an equation of motion. And arguably the goal of physics in 99 out of 100 circumstances, the goal is to develop the particular equation of motion for a particular set of circumstances or conditions. So for example, okay, you'll look at the bottom of the sheet, it looks like something's crossed out at the bottom of the sheet, and it is for a reason, because it's at the bottom of the sheet, it says like an example, well, it says an example of a function which would fit the desired form, but which would not work here is colon, and then there's this blue equation. The blue equation is your good old x equals 1/2 at squared plus v naught t, like that old equation from physics 203. I'm using it as an important example here. I'm saying x equals 1/2 at squared plus v naught t is an example of what we would call an equation of motion. It does have the desired form. It is an example of the type of thing that we're looking for as an answer to question 9. We're looking for x as a function of t. We're looking for an equation of motion. And in the old days, one of our big favorite go-to equations of motion was that one, x equals 1/2 at squared plus v naught t. The thing is, that equation was the equation of motion that we would use whenever we had a constant a, when we had a value for a that we could plug in and rely on for all values. Then we could use that x equals 1/2 at squared equation. An example of that was like free fall. When something is in free fall, it falls near the surface of the earth. It falls at a constant rate of acceleration. So x equals 1/2 at squared plus v naught t is an example of an equation of motion that fits the condition of free fall. We're now in physics 204. We have a new condition here. The new condition, it's no longer free fall, it's no longer constant acceleration, it's harmonic oscillation, specifically an object that is being subjected to or governed by Hooke's law. So what we're really trying to do now, we're just doing typical physics, like find the equation of motion for a specific circumstance. What's the circumstance? Hooke's law. That's what we're doing now. So it's not a joke. I mean, it's like it's real. It's a simple question, but it's not an easy answer to arrive at. So I'm just turning the page here. Right. So here we are. So I'm saying for the harmonic oscillator, A is not a constant because F, the force acting on the mass, is not a constant. In fact, honestly, that's sort of the underlying thing behind all questions 1 through 8. Like we've been struggling with many of the implications of that in 1 through 8. What do we do when A is not a constant? What do we do when A and F depend on X? What we've been doing for like 8 questions really is developing and relying on energy conservation as a way of navigating, because energy conservation is exactly the model deployed when you have a force depending on space. Therefore, and I'm almost done with my yammering, although I always say that and it's never true. Therefore, for questions 1 through 8 that we've been answering, we've been looking at all these relations between, say, force and space. Or put another way, we've been looking at relations between velocity and position. I name the position, you name the speed, or vice versa. That's what we were doing, like in a lot of the questions 1 through 8. Now we're finally saying, okay, that's fine, but can we just what about the basics? What if we name T? Can we name the position? Like, we just really want to know, at any given time, where the heck is this oscillator? It seems like a very fair physics question to ask. Okay, so we've got to deploy the actual specific condition. The condition is Hooke's law here in the middle of the page. Also, Newton's second law is like almost always a condition in physics. So I'm using my 2 pieces of knowledge, Hooke's law, F equals negative kx, and Newton's second law, F equals ma. So, right, and so those are really my step 3, as it says in the right-hand margin here, like that's really my GDP, my general definition and principle is is Hooke's law. Okay, so I put them together algebraically now in step 4, PAW. Side note, please remember always just Newton's second law is the sum of all of the forces acting in a certain axis produce the acceleration in that axis, right? The sum of all forces in a given axis produce the acceleration along that axis. Well, here in the relevant axis, in the horizontal axis that we're looking at here, there's only one force acting. It's the spring force, right? So I just want to caution you again, because it's a common error. Kx doesn't equal F net. Like they don't mean, it's not a triple equal sign. F net means add up all the forces, but there's only one force acting here, and it is the negative Kx force. Therefore, in this case, as you see in the one of the bottom lines of the page, negative Kx equals ma. Like that is to say, Hooke's law is acting on our mass. It's the only force acting on our mass. Negative Kx equals ma. Then I say, oh, okay, and I probably should have left this part blank. So I say negative Kx equals ma. That's an equation. I wrote negative. I'm like solving the problem. Maybe I don't offhand know what to do next, but I say to myself, okay, I say, remember the goal. The goal here is to get x as a function of t. I'm not so concerned about numbers. The example number of the problem happens to be when t equals 1, but that's not the issue really. What I'm really trying to get is some equation that maps t to x. X equals 1 f a t squared won't work because a is not a constant. So I'm looking for x mapped to t. What I have written in the second to last part of the page is negative kx equals ma. I don't want that. I want x mapped to t. So I ask myself, how is a related to t? You might say, or you might think, oh, well, if I remember back to my kinematics equations, like from physics 203, I might think like, oh, average acceleration equals change in velocity per time, like a bar equals v minus v over t. Like I might say, I'm just reminding you, like you might remember or think one sec. Oh, she says hi. Okay, hi. Yes, and her pre-high counted and was disclosed. Her pre-high counted and was disclosed, and the competitor is not here to see the pre-high or the post-high anyway. But yes, okay, no problem. Okay. So I'm saying what I have here is negative kx equals ma. I'm looking for x being related to t. So I think yes, totally. No, she totally wins today. There's no question today at all. But I'm the loser because I got to get back to this before my brain fries. So I think, okay, I don't, on the right hand side, again, I'm talking like right here right now. I'm right here. I'm looking at the right side and I have an a rather than a t. So I think to myself, how is a related to t? Like how is acceleration related to time? I might think, so if you go up and follow the blue arrow, I might think, oh, a bar equals v minus v naught over t. By definition, average acceleration is change in velocity per time. That's a relationship between acceleration and time. But here's the thing, that's average acceleration. We know, and we know here that the acceleration is changing every moment. Whatever the acceleration is at some given moment is not necessarily what the average acceleration is. And it's not what the acceleration was at the beginning. The acceleration's not constant. It's changing every moment. And what I'm looking for in question 9, I'm looking for what x is at any given moment. So I need to know what the acceleration is at any given moment, not just like over time, but at a time. So I think to myself, oh yes, in other words, I need instantaneous acceleration. Like that doesn't say ma bar, it says ma, the acceleration at a point. Well, at a point makes me think of derivatives. Like the instantaneous rate called acceleration is the instantaneous rate of change of velocity. And velocity is the instantaneous rate of change of position. with respect to time, right? Like that's what I'm saying at the bottom here is that acceleration is the derivative of velocity with respect to time. Velocity is the derivative of position with respect to time. Acceleration is therefore, the second derivative of position with respect to time. By definition, I don't know whether you consider this math or you consider this physics, but what acceleration at a moment is the rate at which it's the rate of change of the rate of change of where you are in time. So so I'm going to substitute that in. I'm saying the definition of instantaneous acceleration is the second derivative of position with respect to time. Now notice that's really good for a couple of reasons. Not only just that it has hold on one second. Hold on one second. I'm sorry. Okay, sorry. I'm saying I'm going to make a substitution here. Well, okay, I'll turn the page. Here's the substitution. I'm saying I'm going to substitute in d2x over dt squared for a. Like that's a second derivative, right? But that's good. Not only is that going to bring x's and t's into my life, but notice it literally. Notice. I've got to. Notice, sorry, I'm totally, notice it's not just that it has x's and t's in that expression for the derivative, but please remember the way derivatives are written. Like derivatives are rises over runs taken to the limit, right? Derivatives are slopes taken to the limit. So whatever is in the numerator is this axis of a graph. Whatever's in the denominator of a derivative is this axis of a graph. So whatever's written in the denominator is being treated as the independent variable. And whatever's being written in the top of some derivative is the dependent variable. That's what we want here. We're interested in x as a function of t. Okay, so I substitute that in. So now I have negative kx equals m d2x over dt. Now we're getting somewhere here. We are getting somewhere. Now I want to remind you again, please let's keep our eye on the prize because this is a thick problem or it will eventually maybe seem thick. Let's keep our eye on the prize. Again, for anybody who just tuned in, this is question 9 of homework 1. And the way question 9 is phrased is like at t equals 1, what's x? But I'm saying the real way we're really treating this question as physicists, what we're really trying to do is get x as a function of t. Like we're trying to derive we're trying to derive. Yeah. No, I know, but that is funny, but right, but we are. And let me just say, I mean, I know that's kind of a joke, and I was kind of addressing this before someone got off the subway. Oh, did I just say, oh, but no, all right, fair. No, and it is hilarious. And actually you're pressing, okay, I'm going to address this now. This is what you get for making that kind of joke. No, to everybody again, I mean, that is a funny joke and it is funny. And if I were in the class, I'd be like, what? And frankly, part of the reason I keep saying over and over again, this is homework 1, question 9 is because, right, if I just were tuning in now, I wouldn't believe it either. It is crazy that we're still, I know it's very unusual, and I'm a little defensive about it, but I just want all you to know that unusual or not, it's an unusual choice that I make about how to teach this class every semester. I've chosen to just assign this one homework that has all these things in it and as an excuse so that I can teach all these topics and have you know where I am at all times. Like, just so you all know, and maybe that's really annoying. It could be super annoying to many of you that we're still on the first homework, but just so you know, it's not because you've fallen behind. No, okay, cool. Okay, no, and you're being very polite. And I'm not trying to single out my issue already. I am defensive on it because I know it's weird, but I at least want, you know what I want you all to know as a scientist? I want you to know that if it's an error for us to still be on homework 1, it's a systematic error, not a random error. Meaning it's not because you fell behind or I fell behind this semester. It's the way I do it every semester, for good or for bad. And of course, one benefit is you don't really have to be doing any other new homework while we're doing this. But yeah, just so you all, and just so you know, even if you think it's crazy, you're not crazy. And we're not, it's just the systematic craziness of how I've chosen to do this course. So, oh yes, now that's good. Oh, Maisha's totally like saving. She's totally like redeeming us both. Yeah. And you spend like 2 or 3 labs trying to unpack ideas that are in homework 1. Like really what I'm saying to everybody, and I'll get back to it now. I mean, and look, I'm glad she's noticing. I'm glad any of you are noticing. Again, it might be weird, but yes, you're in the right place. If you're like, wait, we're still on homework 1. Yes, we are. Like, you're not crazy. And if I'm crazy, I'm systematically crazy, not randomly crazy. I don't even know what that means. But the thing that we're spending all this time on, everybody, both all your early labs and this homework, it's all about harmonic oscillation, which honestly is a huge topic in physics for the rest of your life. It's a huge topic in PChem. It's really helpful to get your mind around the mathematics and the physical implications of harmonic oscillation, because like, I'm going to say this one other different way, and then I'll move back. But again, I'm a defensive guy. What can I tell you? It seems like we're spending all this time on like a freaking mass on a freaking spring going back and forth. And yeah, even I'm like, that's kind of boring. You're going to spend a month on a mass on a spring. What's really happening, everybody, is we're spending a month on the mathematics underlying any system that behaves like a mass on a spring. That includes, for example, small angle pendulums, as I think you've seen in the lab. That includes water molecules. That includes something called resistor capacitor circuits. Like there's we're really looking at the harmonic oscillation system in general, and it comes up all the time in nature and in technological devices. The harmonic oscillator is a major important system, really, honestly, in the world. And the harmonic oscillation equations, which we're trying to unpack right now, govern a huge portion of the world. And one thing to understand about all harmonic oscillators is that a harmonic oscillator is any system that ultimately behaves like a mass on a spring, or which means in all of these mathematical ways. So we're studying the mass on a spring as really a metaphor, or as a prototype of mass spring type behavior in general. General mass spring behavior we ultimately call harmonic oscillation. So anyway, so that's what we're doing right now. And what we're really, yeah. Well said. Yes, actually very well said. Very well said. I'll be even more specific. Okay, I'm even gonna write in the chat because that was so good. And as long as I'm gonna think, I'm gonna give you other definitions as well a little bit later, but right now, that's absolutely. Okay, I like that Maisha just said, like, so a harmonic oscillator is like anything like with a restoring force, and well, yes, but now look, but honestly, if you look at like the paragraph right before Maisha's last paragraph, I'm going to say from here on in, a harmonic oscillator is any kind of system subjected to a restoring force for which the restoring force is like directly proportional, or in other words, linearly dependent on what right now I'm calling position, what for a pendulum would actually be angular position, what in general in life is going to be any dependent variable. Okay, I'll even write that too, as long as we're me make something very clear now. There was like, obviously there's a little joking, a haha going on for a minute, but now I just want to say to everybody, this is not a tangent anymore. This last bit that Maisha just said in the chat is actually helpful enough and like important enough that I'm responding in the chat to everyone on purpose so that you can write this down in notes or whatever. Like, this is not a side chat. This is definitely a really good clarifying point that I would have had to have made a little bit later anyway, but it's more contextual to make it now. We're looking at simple harmonic oscillation here. You're looking at it in the lab with pendulums. We're looking at it here with masses on the springs. It's going to come up later in RC circuits, whatever. And it's totally going to come up in your life in PChem if you haven't taken PChem yet, like in a big way, in an atomic way. And I have found in experience that people have a lot easier time with PChem if they realize that that's what's going on when they take PChem. But what I'm saying is a harmonic oscillator is a system that is subject to so please look in the chat is what I'm saying. Like the part in the chat right now, if you often tune it out because it's like all jokes, it's not a joke right now. Like a harmonic oscillator is a system that is subjected to a restoring force, i.e. yes, a system where if you pull it to the right, I mean, if you displace it to the right, it gets pulled back to the left or vice versa. But very specifically, for it to be a harmonic, like any system that has a restoring force will oscillate somehow, but to be a harmonic oscillator, to be the kind that we're really looking at here, the restoring force has to be linearly dependent on displacement from equilibrium position. In other words, the restoring force has to be linearly dependent, directly proportional to the extent to which the system is unrestored. So like in the case of a mass on a spring, F equals negative Kx. It is, the negative means it's restoring, and the Kx means that the force is directly proportional to however much you're not restored, like you're fully restored when X equals 0. Now in a pendulum, the displacement isn't technically position. It's not like technically position on a meter stick. It's angular position. It's like theta. But still, with a pendulum, the reason a pendulum will oscillate harmonically, it turns out, is because the restoring force of gravity, or the component of gravity that acts as a restoring force in a pendulum, turns out to be, and you sort of have to prove this at the end of lab 2 or something like that, or at some point you're asked to prove this, the restoring force turns out to be directly proportional to theta. Ultimately, what a harmonic oscillator is any system for which the restoration of some variable is directly cool. Okay, great. I'm psyched. So that means things are really happening. And go you and go Professor H. Walters. Like, yes. And this is not an easy point. I'm screaming now because it is that important, but it's also like subtle. I literally remember when this point sank in and made sense to me in college. And I know for a fact that the moment it sank in and made sense to me was 2 months, at least 2 months after it was supposed to. Like it sank in with my brain after I took and did very badly on the exam. Like I remember that, and sometimes things took a lot longer than 2 months, that's for sure. But I remember totally not getting this until I got it. But I didn't know I didn't get it until I got it. And then in retrospect, I was like, oh, I totally did not get blah, 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 blah. Like you don't get what you don't get, right? So I'm saying to everybody, a harmonic oscillator can be of any variable. We're going to see other examples. It could be temperature. Temperature could be fluctuating back and forth in a system. But as long as the changes in the changes of the temperature are directly proportional to the temperature itself, then temperature will harmonically oscillate. So, I mean, Mike's just totally right. Like it's all about the restoring force. I'm just adding the very specific mathematical crucial qualification that the restoring force has to be directly proportional to whatever it is restoring in order for us to get all these cycles and patterns and derivatives and everything that we call ultimately harmonic oscillation. Okay, so very good. Yay, everybody. Yay. Spelled backwards is yay. So now, so what are we trying to do? What are we trying to do in question 9 here? What we're trying to do is something that is very simple to ask. It is not easy to answer. It's like a very real deal. We're asking, what is the equation of motion for a harmonic oscillator? What is the x as a function of t for something that obeys a restoring force of this kind? Well, how far have we gotten so far? We got to this second line, like where I am right now. I need a way. I need like a, oh, can you see? No, you can't. Okay, hold on. Where I am right now, I'm right here. Okay, oh, that's, where the little stupid blue arrows. What we have so far is negative kx equals md2x over dt. Now, we're not done. That's not a final answer yet, but it's good progress. It's good progress because if, as you see from my annotations, like there's only two variables in that equation, and they are the exact two variables that we're interested in, x and t. And in fact, they're being treated by that equation in the proper way. Like x is being treated as a dependent variable and t is being treated as an independent variable. How do I know? Just because of the way that derivative is written, okay? Like the numerator and the denominator. So, and anything else in that equation, there are a bunch of other letters like k and m, but they are constants. They're not variables, they're constants. So that's good. Like, in other words, we have a package right now that has the information in it that we are looking for, but it is packaged in a funny way. Oh, good question. I don't know if is that a public question or a private question? So the units for x in this context, good question. In this context, since we're talking about question 9 on homework 1, so we're talking about the mass on the spring here, the x that, oh, so sorry. So in the chat, Maisha asked, what are the units for x? The answer is meters. Because here by x, we really do mean, we mean position relative to the equilibrium position of 0, like x naught. We're talking about that mass on that spring that's going back and forth and back and forth that had an initial value for x of 0.15 meters. Yeah, wait. Oh, x, I mean, so the units of x, yeah, well, so the units of the dependent variable do depend on the scenario. Here, whether it's meters or centimeters, I mean, we generally like to be in MKS. So generally, if x is measuring position, I mean, we would generally ultimately want it to be in meters, especially because, like, if we're talking about a mass on a spring here, for example, K is in newtons per meters. So if it's a real displacement, we would generally like it to be in meters. If you're making measurements in the lab, you might make the measurements in centimeters, but then you probably should convert them to meters before you plug in. X, in this context, X is generally assumed to be a displacement. So it's measured in meters. It is true ultimately with all of this harmonic oscillation stuff, all this math, ultimately, X might be some other variable like theta or Z or E or something. And then it might have other units. Like it's definitely true what Maisha is asking, like the units of the variable could differ from context to context. Yes. Here, right now, I'm in question 9 of homework 1. Definitely X is in meters as far as I'm concerned right now. I don't know if that answers or not, but I mean, it's always good to pay attention. Oh, in fact, yeah, I mean, that is my answer. I'm overthinking her question, I think, but units will certainly matter. Like I can always get behind a units question. I mean, and they are going to matter in this analysis. Oh, no problem. Okay. All right. I'm going to shut up. I'm going to keep going. But yeah, good question. And the answer is meters, and they will matter. You're totally right to ask. I don't know what my problem is. Well, I do know what my problem is. Ask my parents. Okay. So right now we have negative kx equals n d2x over dt. But, you know, there's this like derivative sitting there that's sort of annoying. Like we weren't asking for anything about a derivative. We were asking what's x as a function of t. And then suddenly this, not only derivative, but this second derivative is popping up and sort of like clogging up the works. So we got to do that thing in physics that we always do that is sometimes psychologically not appealing. The part of this whole situation that's clogging us up, that's sort of unexpected or confusing or that seems to be getting in the way, we should isolate and focus on. That is, I didn't ask for a derivative. I asked for x as a function of t. So, but suddenly there's a derivative there. In fact, a second derivative there. So I'm going to rearrange things and actually focus my attention or focus the expression on that derivative. Because I got to do something to it. It's in the way, or it's important somehow. So it says here, let's rearrange and focus on that derivative. Okay. So I've rearranged the whole equation. I've packaged all the constants together as parentheses k over m. So now I have this equation d2x, and this is the equation that I sort of keep on writing on the first page of notes, like every day. This is like an important equation now. d2x over d2t squared equals negative k over mx. Now, so the left side is a derivative. The right side is a linear function of x. It's a bunch of constants times x. Now, that is not the answer. That is not the answer. And again, it's not because we're off on a tangent. This is a thick question. That is not the answer, but that is an important expression. It's an expression that relates second derivative of x with respect to t to x itself. It's got all the information in it that we want. It's got like x as a dependent variable. It's got t as an independent variable, but it's not relating them the way we want. What we want is like x on the left side and blah, 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 t on the right side. So this is not what we want, but this seems to be important. And it's this thing that we're going to have to unpack somehow to get what we want. So I'm going to turn the page. Okay. So there it is. I've just rewrote it at the top. Okay. So now I'll just read out loud what I wrote in blue here. We'll just notice. So on the left is a derivative, right? It's a derivative. I should say, in fact, on the left-hand side of the equation is derivative of x with respect to t. And truthfully, yes, it's a second derivative. So I mean, technically it's a derivative of a derivative of. But notice the left is derivative of x with respect to t. X we're treating as like rise and t we're treating as run. Then on the right side is x is a variable, the dependent variable x. So what did I write in blue? I wrote the above equation expresses a second derivative as a function of a dependent variable. It's expressing derivative. It's like it says, if you tell me x, I'll tell you what the second derivative of x with respect to t is. Like that's what that expression is saying. Again, that's very interesting and important and helpful, but it's not what we're asking for. What we seek, it says in blue here, what we seek is dependent variable as a function of independent variable. Like we want a regular function. We want you plug in t as the input, we spit out x as the output, right? We want x as a function of t. What we seem to have here is second derivative of x with respect to t as a function of x. We're making progress, but we have to do something to this equation to unpack it, to get it in the form that we want. Now, we can't just do algebra. We can't like just like multiply both sides by dt squared or something like that, because it's not, dt squared is not a variable, it's an operation on t. Like you can't just do algebra on this and isolate the x. Maybe you could do calculus. In fact, we better do calculus, because again, what this is saying, we thought we wanted x as a function of t. What it's giving us is derivative of x with respect to t as a function of x. Now, if you're thinking anything like this, I'm going to be very, very careful here. So let me say it one more time. We're looking for x as a function of t. We're looking for a function. What we're being presented with here is instead of the function, we're being presented with like a derivative, a second derivative, in fact. If you're thinking anything at all, if your brain is saying anything about integrals or anything about the fundamental theorem of calculus or something like that, or if your brain is doing anything like, can we do antiderivatives or something? Then first of all, yay, like good. Then you're totally with me in a way. I mean, well, honestly, and that's funny too, but honestly, the calculus is about to get bigger now, not smaller, to be honest. So bear with me for a second. Yeah, no, and I do feel your pain, and I'm kind of laughing, but I'm not even going to like laugh too hard right now, because to be honest to everybody, this is where this course is a lot more heavier in calculus than physics 203, honestly. And again, let me just say, like I think I've said in this class before, I'm not here to assume that you guys are totally comfortable with calculus. I'm not here to assume that you all rock at calculus. I'm not here to assume that you love calculus. Honestly, from my experience doing this, I assume the opposite of all three of those things. I know you've taken calculus. I know it was a prerequisite for the course. I do not assume that that means that you love it or that you feel that you've mastered it. In fact, quite honestly, what I really think generally when people come to this course, they've done a lot of calculus. There's certain kind of problems that they can solve, but first of all, they don't like solving them a lot of times. I'm not speaking to everybody. I'm just speaking for a lot of people when they come to this class have done a lot of calculus because they were required to, have solved a lot of problems, might even have done well at solving those problems, but A, don't necessarily like it, B, can solve the problems that they were asked to solve, but wouldn't necessarily know how to cross apply that to any other course, or wouldn't necessarily know why they were solving those problems, or really even how, like, or why the theorems are true, or why the problems like apply to anything in real life, or where the calculus came from. I assume that a lot of people come here not feeling comfortable in all those areas, in any of those areas. And I assume, by the way, that there's some people that are uncomfortable in all those ways and don't even know they're uncomfortable in those ways. I am not assuming that you guys love calculus or have mastered it. Even those of you who think you have might not. I am here to say, oh, well, no, I'm not here to say, oh, well, I'm here to say calculus does become a very big piece of physics. Physics 203 is kind of the warm up or the ramp up. Calculus is a very real element of physics 204. I'm not here to assume that you already get it, but I am here to assume that you can give it a final chance or a final shot, or give yourselves a final chance. I'm here to assume that physics 204 is the place where a lot of people, including me, actually finally start understanding certain aspects of the calculus and maybe even liking them, maybe. And it's about to happen right now, or we're about to attempt that right now in even a bigger way. So bear with. So maybe that's an apology, or maybe that's a like, let's go. But just because I'm really here to say, I don't care how uncomfortable or unmasterful you might feel with calculus right now. I'm not assuming that the prerequisite means anything other than you've seen some stuff before, but I'm here to say we can still get it. And for me, I did not get the calculus nor like it until I had to see it and practice it a number of times in physics. So this is a chance for some of you. It is a chance for some of you to actually take a fresh look at it and maybe start appreciating it or seeing it in action. Maybe that won't work for a lot of you, but please don't assume it's too late. That's what I'm definitely trying to tell Maisha and everybody. It is not too late to appreciate or get better at calculus. It is not too late in any sense of the word. This is the opportunity. So here we go. And today won't be the last class either. But so what I'm saying is, we have a situation here where I'm looking for a function. I'm looking for x as a function of t. What the physics spat out at me, not a random math problem in a textbook, not a math teacher. And obviously I have great respect for math teachers, but it wasn't a math exercise or math context that spat this equation out. It was just pure physics. It was just like, we just plugged Hooke's law into Newton's second law, and then we get this thing with derivative, and we plugged in the definition of acceleration, and we just get this thing that has a second derivative in it. We're looking for x as a function of t. Instead, we're facing derivative of x as a function of t. So some of you might be saying, well, based on a lot of what Yavrban was yammering about last week, I suppose if I'm looking for the function, but I'm given the derivative, I suppose I need to unwind that derivative. I need to invert that derivative. I suppose I need to do that derivative backwards, you might be thinking. And so far, I agree with you. Like, it's not that I'm asking you to take a derivative here. In fact, very much not. I'm asking you to understand derivatives in a way. I'm not saying we got to take a derivative. I'm saying we're given a derivative. We're given that the second derivative of x with respect to t is equal to this expression, negative k over m times x. We don't want that. We want x as a function of t. So we want to undo those derivatives. We want to invert them. We want to do the inverse function of them. We want to anti-differentiate in a way. So if you're thinking, oh yeah, that's the fundamental theorem of calculus. Oh yeah, the fundamental theorem of calculus says that the integral is the antiderivative of the function. Then you're right. And then you have been paying attention, and that's very good if you're thinking that. And you're so right that if the right-hand side of this equation just had a t in it, like instead of where the x is, if there was a t, if it said the second derivative of the second derivative of x with respect to t is equal to blah, 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 negative k over m times t, then we would literally use a fundamental theorem of calculus. We would integrate once and integrate twice, and we would have our answer. If that makes any sense to you at all, then you're definitely been doing something right in this class or in calculus. If you're thinking, well, we have two derivatives, but we want the function, I want to undo both those derivatives, so I'll integrate twice. You are thinking something very smart, very wise. But here's the really bad news for Maisha or anybody else is that's smart thinking, but that's actually not going to solve our problem here. What we have here is actually something even harder than that. And it's not because I'm trying to make your life hard. It's because the physics situation just is simple, but not easy. What we have here is that the second derivative doesn't depend on the independent variable. It seems to depend on the dependent variable. That actually makes all the difference in the world. I'm going to flip the page in a second, but just to read what it says in black at the bottom of this page, what it says in black on the bottom of this page, it says if IFF, like if and only if and only if the variable, wait, I'm going to get that chat in 1 second. Let me just say this. It says at the bottom, if the variable on the right-hand side were the independent variable, i.e. t, if that variable on the right-hand side were t rather than x, then we would need merely use FTC, fundamental theorem of calculus, and we would integrate twice if the variable on the right-hand side were a t. Now, let me say again, what's special about t compared to x? What's special about t is that it's the independent variable. Am I saying that t is always the independent variable? No, I'm not saying that at all. In fact, in 2 of your labs, it wasn't. I'm saying that I know in this context, t is the independent variable for 2 reasons. One, it's what the original question asked. It said, given t equals 1 second, what is x? Like the whole nature of this question is that we're trying to relate x as a dependent variable to t, the independent variable. But the other reason I know that t, the independent, is the independent variable is that it's written in the denominator of that derivative expression. So if the right-hand side had the independent variable t in it, then, for those of you who are following this, then indeed we would merely need to anti-differentiate twice. We would just have to unwind these 2 derivatives, i.e. we would simply integrate 1 time and then 1 time again, and we'd be good to go. We cannot do that here. The situation here is a little bit more interesting than that because we have a derivative that in fact is depending on the dependent variable. Bizarre. Let me just check the chat because I think that was legitimate. Oh, interesting. Fair question. Sure. Wait for the homework one. Sure, I can make right now, everything is about the homework one. So the playlist that's called P204, SP22 is all about homework one, yes. But once I move to homework 2, sure, I can take out all the homework 1 ones and make it one playlist. Sure, yeah. Maybe remind me, but yeah, no problem. Thank you for being interested. Yes. So let me go to the next page here. And again, I'm going to warn you right now. Again, this is now deep stuff. This is real stuff. It takes a while to talk about. I mean, I could have assigned 1 million exercises and made homework 1, I suppose 5 homeworks. I just didn't, for good or for bad. But please understand that I'm not going to finish solving this today. I'm trying to explain it. And I am trying to explain things that I do know mystified me or confused me for a long time. I'm hoping to try to break these things down for all of you. Please know in advance, we're not going to get an answer to this today. And it's not because you messed up or I messed up. It's not because we're off on a tangent. This is the subject material. And for my mind, if you go on in science in any way, or even just a PChem and instrumental, I think this understanding will serve you well. That's the choice I'm making. But so if you're following, if you're still with me here, and I apologize also if you're like a little bored or whatever, but if you're still with me, please know this is not a digression or like this is not side topic. This is the topic. It's just a thick one that went way too fast for me when I was a student, really. So maybe I'm going way too slow now. I don't know. But I'm going to go to the next page. The next page is So, all right, so this expression, so we have this expression, the one in brown, we have d2x over dt squared equals negative k over mx. Now I'm going to tell you right now, this expression, which is not our answer, it's now a project for us. We have to unpack this expression. This expression is our first example in this course of something known as a differential equation. It happens to be, in fact, known as a second order differential equation. I have to pause on that. First of all, it's called, so that's what it says in the middle of the page here. First of all, it's second order, which sounds very intimidating in itself, perhaps. It's second order because the derivative on the left side is a second derivative. If the left side just said dx over dt, then it would be a first order differential equation, okay? You might even say, why are we starting with, like, oh my God, like, wait, you might even say something like, I've never even done differential equations before, which I expect is the case for most of you. You might be saying, wait, was I supposed to take a class in differential equations? No, you were not. You're supposed to learn them here with me. If you had taken a class, I would be afraid, I think that would actually mess you up and would make this harder for us, to be honest. It's totally not expected that you've ever taken a class in differential equations. Such classes do exist. It's also not expected that you've ever explicitly confronted differential equations before. I'm going to show you what you need to know, what we need to know about them now in a physics context. And again, that's not by mistake. And it's not to be like mean. It's because the physics is presenting us with differential equations. Like, we're staring into nature, and what's spitting back is this thing that Newton had to solve and Hooke had to solve, and they didn't know anything about differential equations. They just had to work it through. And then in retrospect, these things became called by mathematicians and so forth differential equations. One thing you might say is, why are we starting with, well, I mean, if we have to do this, why are we starting with a second order? Couldn't we do a first order first? Wouldn't that be easier? We might, if we want, if this gets bogged down, if it becomes, if you want, like next week, we can back up and do a first order one. Sometimes I do that in order to practice or get people familiar. But the reason we're not starting with a first order is because this is not a math class, because it's not supposed to be a whole big lesson, the whole big wide world of differential equations. We're just trying to solve what we see in the physical world of physics. So the first differential equation that pops out to us in physics is this one, d2x over dt squared equals negative k over mx. What it really is Hooke's law, or like Maisha said, it's just a restoring force equation written in mathematical kind of symbols. So this is a differential equation now, and we're gonna unpack it here. We're gonna start unpacking it here. I just wrote in the black, like, again, sometimes if people are tuning in and out, they suddenly get freaked out when they see that word. Please just note, the math course is not pre-required for this. It's expected that you've seen derivatives and seen integrals before. It's expected that you don't love them. I'm trying to get you to like them more. It is not expected that you've seen differential equations before. If you ever have and you want to privately chat with me and tell me that you have, great. And then hopefully they didn't corrupt your brain, but it's not assumed. I'm here to teach you something, not to hold you responsible for something in your past. But let me tell you what I mean by a differential equation, because we do have to solve at least one, or at least I have to show you the solution to at least one. A differential equation does not just mean any expression with a derivative in it, frankly, or a differential in it. Frankly, for the longest time, I was a physics major in college, so I had heard for a while I was going to have to take this big bad math course called differential equations, and I had heard that physics gets very into differential equations, and I was kind of scared. But I was also kind of confused and annoyed because I kept thinking, why do they keep? I had taken already 3 calculus courses before we got to this thing called differential equations. And I was like, why do they keep making a big deal about this? I mean, are they just trying to bother me and scare me? Because like, I've done a million equations that have derivatives in them. Like, haven't I done a million differential equations? And what I'm here to tell you is that the strict definition of a differential equation is not just any equation with a derivative in it or a differential in it. A differential equation is what it says in illegible brown at the bottom of this page. It says DifEqs, differential equations, relate rates of change, i.e. they relate derivatives, to dependent variables. Like, notice this thing at the top. I'm saying I'm saying the thing at the top in brown, d2x over dt squared equals negative k over mx. If that x had been a t, then technically, I suppose you could call it a differential equation, but nobody would. If that x had been a t, then it would just be an equation that has a second derivative in it. And we would just integrate twice to get the answer. It wouldn't merit a whole big 45-minute discussion like this. It wouldn't merit a whole course or whatever. If that, and it's that big of a deal. If everything else had been the same, if everything else had been the same in that equation at the top, except for the x had been a t, then I don't have to say all of this at all. We would just use the fundamental theorem of calculus. But the fact that that x is an x, the fact that we're relating a rate of change to a dependent variable is what prompts investigation. Differential equations, some are very hard to solve. Most are totally unsolvable. Some are solvable. Some we know are going to be solvable when we look at them right away, we know, and then we start working on solutions. Some we don't even know if they're solvable or not until we look at them further. Differential equations are like integrals in that the way to deal with them is to develop a bunch of tools and techniques and experience and different experiences and different tools for different differential equations. There's no one steady, reliable algorithm or procedure or just memorizable set of rules for unpacking differential equations. They are a world unto themselves. We are going to deal with some in this class, not all of them, not a million, just the ones that physics makes us solve. All differential equations capture or express something that I wrote here at the bottom page called feedback. Let me tell you what I mean. Hold on. Oh, yeah, okay. Let me tell you why. In other words, so now I'm going to tell you why differential equations are a big piece of physics, and why they're important and why they're interesting. And they're not impossible or anything like that. And I don't mean any of this to be intimidating, but I'm saying they're worthy of consideration. They are a thing unto themselves, differential equations, precisely because they relate rates of change to dependent variables. If you think of an independent variable as like a cause, or like an input, but kind of like a cause, and you think of a dependent variable as like an output, or in other words, like an effect. If you think, and there's a loose like analogy, but if you think of independent variable as a cause, and you think of dependent variable as like effect, then what a differential equation does is it says that somehow a rate of change of effect with respect to cause is somehow related to or a function of effect rather than cause. That is right. I'm saying the rate of change of the rate of change here at the top equation, if you look at, is somehow a function of it's equal to negative k over m times x times the dependent variable times the effect, not times the cause. Let's put that in English. It's an interesting idea. What we're saying here in mathematical terms is we're saying someone's coming along and asking, what's x as a function of t? And that's still our equation. Sorry, that's still our objective, our goal here. In fact, let me write that before we forget again, which is very possible. Hang on. I'm going to keep saying it because it's so easy to forget, I think, or so easy to lose perspective on. Remember that what we're seeking is x. So what that says, sorry, if you tilt your head, what that says in blue is the solution we seek is x equals f of t. Like we're looking for an equation here. We have an equation, but the equation we have is not what we're looking for. The equation we have, the differential equation we have, is posing a question to us. It's a problem. We want to solve it. What would it mean to have a solution to it? The solution that we're seeking. We'll know we've solved this differential equation once we get x on the left side by itself and t on the right side multiplied by a bunch of things or operated on somehow by a bunch of things, right? Like we have an equation that is presenting the problem. We're looking for a different kind of equation to serve as the solution. And differential equations are always like that. The differential equation presents a derivative as some sort of function of the dependent variable. We're looking for dependent variable as a function of independent variable. Now in English, what's interesting about this, or what's weird about this is, remember, we're looking for x as a function of t. So it's like I walked in the room and I say to you, hey, if you name the time, I walk into the room and I say to you, hey, if I name the time, can you name the space, the place? If I say, t equals 1 second. Could you tell me where the mass is, please? Can you tell me a position corresponding to that given time that I named? And you say quite rightly to me, you say, oh, okay, you're naming the time. You want me to name position. Oh, okay, I know physics. I know basic physics and stuff. I'm going to tell you that, yes, I could do that as long as I know the acceleration. Like as long as you tell me the acceleration at that time, I'll be able to figure out the position because I know all my physics. I know like 1 FAT squared. I know everything relates to acceleration ultimately, like x equals 1 FAT squared plus v naught or blah, blah, blah. So I say to you, if I name the time, can you name the position? And you say, yeah, if you tell me the acceleration, I can name the position. So then I say to you, and this is what this is really saying, I say, oh, no problem. I could tell you the acceleration. It depends on position. And you go, wait, what? I thought you wanted me to name the position. I go, yeah, I want you to name the position. Like if I name the time, you name the position. And then you go, all right, so tell me the acceleration. And I don't say, okay, I can tell you the acceleration. It depends on the time. If I said that, we'd all be in business. If I said the rate of change of position depends on time, then we would plug in the time, we'd get the acceleration, then we plug in something else and get the position. But that's not what I'm saying. I'm saying, sorry, okay, I just got some, 1 second, sorry. Okay. Sorry. But this is worth repeating. Sorry. I'm saying we want position as a function of time. So you say, no problem, just give me the acceleration. If I said I can give you the acceleration as a function of time, we would have no problem. But I'm saying, oh, I can give you the acceleration. It depends on position. And you're like, dude, the position depends on acceleration, always in physics, and it does. The position depends on acceleration. And now you're telling me the acceleration depends on position. What kind of nonsense is that? That's a circle, right? Do you see? I'm not trying to confuse you people, whoever's still listening to me. I'm not trying to confuse you. I'm trying, in fact, to unconfuse you by saying this is an intrinsically bizarre, confusing situation. We're saying the rate of change of x with respect to t depends on x. Let me give you one final, this is what I mean by feedback. I'm saying the cause feeds the effect, but then the effect becomes a cause and feeds that. It feeds back on itself, like for real. Let me give you another example of the same thing. And I understand there's 5 minutes left. Again, I'm not going to solve this whole thing today. I'm trying to get you to appreciate what it is that we have to solve. Another example of this would be like interest-bearing savings account. You've heard of this in other contexts in math. Like if I walk into a bank and I say to them, hey guys, I have an interest-bearing savings account at this bank. I'd like to know how much money is in my account. And they say to me reasonably and correctly, they say, oh, well, it's an interest, hi, Professor, you have it around. It's an interest-bearing account. So how much money's in your, we got to look up. It depends how much interest was put in last night. Like we add money to this account every day. So like, even though I remember what was in your account last month, if you want to know what's in it now, I got to look up. I got to see how much interest we added to it yesterday. And then I say, okay, that's cool. That makes sense. How much money's in my account depends on how much interest you added to it yesterday. So I say, hey, how much interest did you add to it yesterday? And they, like, how many dollars did you add to my account yesterday? And they say, well, that depends on how much is in your account. right? Like that's literally true. The amount in my account depends on the interest added, but the interest added depends on what's in the account. Yes, yes, yes. It's like, thank you, Elizabeth. That's great. And thank you for, wait. Yeah. Oh, very well done. Oh my God. Like if I had to end right now, I would end on the note that Elizabeth put in the, and thank you for part. Yes, yes. It's like, it's a crazy circle. It's a bizarre, it's not, it is a crazy circle. Always, all differential equations are what Elizabeth with an S just said in the chat. Yeah, something else to get her up, and that something else depends. Right. And the something else, just to quote her, the something else is the rate of change. So like in the case of money, where it's sort of easier for all of us to picture sometimes, in the case of money, interest is the rate of change. It's like the rate at which you're adding money to your account, right? But what's weird about interest is it doesn't, the amount that they added last night just doesn't just depend on time. It doesn't just, if they just said how much we add to your account depends on time, like we add $1 a day to your account. If they just said that, I'd be like, oh, well, 3 days ago, there was $100 in the account. Now it's 3 days later. So there's 103 in the account, end of story. But they don't say that. They say how much actual dollars we add to your account doesn't just depend on the time. It depends on the amount of dollars in your account. The rate at which we're changing your account depends on the amount in your account. It depends, and that's what's happening here. The rate of change, and again, we're going to end in like 2 minutes or 3 minutes, but the rate at which X changes in T, or really the rate at which X changes with respect to T depends not on T, but on X. The derivative depends on the dependent variable. That means somehow cause and effect are looping back on each other. We're getting some sort of feedback. The position depends on the acceleration, but the acceleration depends on position. It's actually, and every differential equation has this quality where the rate at which something is changing depends on the thing itself. That's why it prompts its own discussion. It's actually remarkable that any differential equations are ever solvable. It's remarkable that there's any way to get to the bottom of this, but there is. And different differential equations, this is not a math class. So I'm not here to teach you like all the rules for all differential equations in life. I'm here to teach you like how we unpack this one, which was like the first one that physicists had to unpack. What do we do? One standard technique, and I'm going to flip the page. It's going to be the last page of today because I see there's 1 minute and a half left, and it's all that I want to get to today. One standard practice in strict math and strict science for solving differential equations is, in fact, conjecture. Okay, wait, hold on, and then I have to rush this. Well, right. Well. X is. Well said, mate. Yeah, I had to read that through a couple of times. Right. Really, what X is independent to T? Yes, I mean X is independent to T, and really the rate of change of X is dependent on X. But yes, essentially what May is saying is yes, that is the issue. That it doesn't mean we can't solve it, but that's why it requires all this discussion, because it's like a weird phenomenon. So that's good, May, and thank you. Awesome. So my last thing I'm going to say, the last page and the last thing for today is one method that we absolutely do in math and science for solving these is we conjecture and verify, i.e. we guess and check. Literally, that is a method, because sometimes we don't even have any better methods. Now, guessing doesn't sound like math or science, but once we check, which there is a mathematical and scientific way of doing, then it becomes math and science. Where do we get the guess or the conjecture from? As scientists, we get it from our experience in the lab. So what I'm saying very quickly here with the 30 seconds left is, if you imagine a mass going back and forth on a spring in the lab, you imagine taking time, like every second, asking where the mass is. The mass would start over here to give me like one, I know it's 4:20, just give me like 30 more seconds and then I'm done. But just imagine the mass starting somewhere away from equilibrium and letting it go. So it starts moving toward equilibrium and then past equilibrium to the other side, and then it turns around and comes back. Just like everything we were saying in questions 1 through 8, it would go back and forth on a graph. If time were on your independent axis and position were on your dependent, you would see the thing going back and forth on the graph like a cosine function. So we're going to guess, and this is as far as we're getting today, we're going to guess, conjecture, that equation of motion is some sort of cosine function, only I put blanks before the t and before the cosine entirely because of something Maisha said like 40 minutes ago. And this is where we're going to end, which is that, okay, x is going to be some sort of cosine of function of t. I'm guessing. We'll have to verify to find out. But I'm a scientist. I care about units of measurement, as does Maisha, as does May, as does Elizabeth with an S. I care about units. So I can't take the cosine of a second. I'm going to have to put something, some kind of constant before that time, right? I'm going to have to put some sort of constant right before that time to change the units from seconds into something like radians or degrees or something. Similarly, I'm going to have to put a constant before the cosine because cosine spits out numbers like 1 or 0 or 1/2 or √3/2, but it doesn't spit out meters. And our ultimate answer, like Maisha asked a while ago, our ultimate answer for x has to be in meters. So there's going to be some kind of constant before the cosine and some kind of constant before the t to adjust the units. That is my conjecture, my guess to the solution to this differential equation for right now. That's all I've got right now is a conjecture, and it's not even fully complete. And that's where we're going to end today. And I have to go to another class, I have to cover another class right now. So thank you all very much. There's no new homework, blah, blah, blah. I will catch up to you. I'll hang out for a second if there's any questions, but then I've got to go to, so thank you. And I'm turning off the recording, but thank you. Thank you guys. And thank you, May. Well done. Thank you all, everybody. But okay. Yes. And see you as, yes. And thank you, Maisha. And thank you, Elizabeth.
Have a good one.
Thank you, you too. And thank you, everybody, for real. But thank you, in particular, those people who participated. Who else? But I'm turning off. Bye, Lizzie. Thank you. And that's participation. That is. And thank you for being first. I know you were like, okay, I'm turning off the recording and the blah, blah, blah. Hold on.